In 2.4, we're going to talk about uniform circular motion. And uniform just means constant speed. So maybe you stay at 55 miles per hour. You're just going to keep that the whole time you're going in a perfect circle. Just to point out that even though it is constant speed, it is not constant velocity because its direction is always changing. So that velocity arrow is always turning. So that means there is an acceleration. And that means that there always has to be a force causing it. So like maybe you imagine the Earth going around the sun. The reason why it can travel in a circular orbit is because gravity is always acting on it. Or if you imagine a car going around a freeway entrance ramp, going in a circular path on the ramp, you have to grip the road, you have to have friction in order to actually move in a circle. Otherwise you would just skid off in a straight line and end up in the ditch. So I'm going to start off with that actually as my first example, and I'm going to imagine a car and imagine that this is just a view from above. So I'm looking down at the car, and initially they're here, and then they're going to drive around the curve and they're going to end up over here at some later time, still moving forward at constant speed. So for constant speed, I tried to draw the velocity arrows the same length, but you'll notice again here that they're in different directions. The velocity in this case is always going to be tangent to the circle. So if the car is right here, at that instant, they're moving straight on the road at that point. But then by the time they end up over here, and they have to follow the road this way, their velocity would change to be in this direction. So that's what this acceleration does, is it's always going to be tipping that velocity arrow, tilting it more to one side. So the velocity is going to be tangent to the path. And like if you lose grip on the road, if you lose your friction there, the car would just skid off in a straight line. So if you want to go in a circular path, you have to have an acceleration. For these cases of uniform circular motion, the acceleration is always pointing to the center of the circle. So if you imagine the path here is a circle, I've only drawn a segment of it. Right, the center of that circular path would be right here, and so the acceleration points in that direction. So we've talked about the direction of this acceleration, but in these types of cases, there's also an easy way to figure out how strong that acceleration is. So we get a new equation where the acceleration is equal to v squared over r, and this equation is only valid for when the acceleration is perpendicular to the velocity. So basically when you're doing circular motion. In that case, a is v squared over r. And for v, you would just plug in the speed. And for r, that's the radius of your circular path. So if this is the center of the circle, then r is this length. And in these cases, the acceleration is special because it's always pointing inwards. So you can give it an additional title, kind of a special name, and that would be centripetal acceleration. And centripetal just means center seeking. So you can see that the acceleration is seeking towards the center. For section 2.5, let's just skip it. It's called projectile motion. Right, but projectile motion is really just anything moving in an arc while gravity is pulling down on it and there's nothing else acting on it. So it's kind of like free fall, but also moving sideways. So like a football, once it's been kicked, we could say is in free fall, but it's also moving in an arc. So we're just going to skip that. Water flowing out of a hose, we can skip that too. So if you're going to do some extra problems from the book and it references an object moving in an arc, you should just skip it.